Welcome to Thinking Earth. This project tackles major global challenges by using AI and big data to build a graph model of the Earth and the first ever Copernicus Foundation models.
Welcome again, everyone, to this webinar to explain what this ThinkingEarth Hackathon will be about. As you know, and as you have probably read the description at the page of the Big Data from Space conference and the DevPost page of the hackathon, this is organized in the context of our Horizon Europe project, which is called ThinkingEarth. And the full title is Copernicus Foundation Models for the Thinking Earth. This project, in a nutshell, is funded under 2022 call of Horizon Europe, and it is managed by the EU Agency for the Space Program, and it is focused on large-scale Copernicus data uptake with AI and HPC. And the expected outcome of this call is the adoption of big data and AI technologies in the space industry to innovate following industrial requirements and user needs. And the project started in January 2024, and we expect to finish by December 2026. And this diagram is essentially our project in a nutshell. We are using Earth observation data, mainly from the Copernicus program of the European Union. And we treat the Earth as an interconnected complex system, and we apply artificial intelligence methods, building foundation models and a representation of the Earth as a graph. We are using high-performance computing, and we combine the Earth observation data with non-Earth observation data from industry and user partners in order to demonstrate our assets, the foundation models and the Earth as a graph, in large-scale use cases and in smaller scale downstream applications, which we call spotlight applications. We have three main use cases in our project. One is focused on solar energy forecasting. The second is on biodiversity monitoring, and the third is focused on food security understanding. And we aim to create impact in this project and to address several sustainable development goals, including zero hunger, climate action, life on land, affordable and clean energy, and sustainable cities. Now we have 12 partners in total in this project. It is coordinated by the National Observatory of Athens. And we have several partners, including the University of Valencia, Technical University of Munich, the Center for Research and Technology, ELAS, Evenflow Energy Family, NVIDIA, and some partners, smaller SMEs, including an Austrian company, Stadtwerke Amstetten, a French SME which is called Globai, a Spanish company, utility company, which is called Aquatech, and we also have the World Food Program as a partner in our consortium, and the National Technical University of Athens. I am the project coordinator from the National Observatory of Athens. I don't remember if I introduced myself at the beginning. My name is Susanna Tulumzi, and I've been a project manager at the National Observatory of Athens for the past 5 years, and now I'm coordinating Thinking Earth. And in this webinar, we have also representatives of the Technical University of Munich, NVIDIA, and National Technical University of Athens, who are the track leaders of this hackathon, and our communication leader from Evenflow. And now I will briefly give the floor to my colleagues for a roundtable introduction, starting from the Technical University of Munich, that is leading the first track of this hackathon. If you would like to share a few information.
Good morning, everyone. My name is Yi, and I'm a PhD candidate at Technical University of Munich, leading the scientific development of Copernicus Foundation models in this project. And I'm also gonna present today a short webinar introduction about the first track, Earth observation foundation models, and looking forward to the later part. Yeah, that's it.
Thank you, Yi. And the leader of track 2 is Franziska Gerken from NVIDIA.
Exactly. Hi, everyone. My name is Franziska. I'm also a PhD student. I'm also affiliated with the Technical University of Munich officially, doing my PhD over there. I'm also a research intern at NVIDIA. I'm working with Laura Leal-Teché together, and we are leading the work package Earth as a Graph in the ThinkingEarth project. And we're also responsible for the track 2 of this hackathon. So we're gonna explore like the weather forecasting models, together. And I'm also really looking forward to the hackathon.
Thank you, Franziska. And the leader of track 3 is Angelos Avras from the National Technical University of Athens. Hi, Angelos.
Hi everyone, my name is Angelos Avras. I am a PhD candidate in the National Technical University of Athens, and I will later present more about the track number 3.
Thank you, Angelos. I will wrap up this presentation to explain a few things about the hackathon, and then we will go to the presentation of the tracks. So to summarize the objectives of the ThinkingEarth project, which are also partially related to this hackathon. So our core objective is to research and develop our AI methods that treat the Earth as a complex, unified, and interconnected system. And to this end, we have 4 sub-objectives, let's say. One is to develop the first Copernicus Foundation models. The second is to develop a deep learning representation of the Earth as a graph using graph neural networks. The third is to apply causality and causal inference methods and explainable AI to solve Earth system science problems. And the fourth is to develop scalable products utilizing Copernicus and industrial and user data and create new value chains in renewable energy, biodiversity management, and food security. And this fourth objective is directly related to the scope of the 4 use cases that we have designed. The first one is on distributed solar energy production, forecasting, and demand management. The second is on biodiversity monitoring in urban environment. The third use case is on forest biomass monitoring and more specifically, the estimation of carbon stock in the carbon credit industry and the estimation of above ground biomass to assess forest carbon stock. And the fourth use case is the causal inference application for food insecurity analysis. Now you can find more information about our project. Please follow us on X and on LinkedIn, and you can also visit our website and subscribe to our newsletter to get updates and information. We release a lot of material frequently, our papers, our scientific publications, milestones, and all the developments to the scientific community and to the public. Now, what is this hackathon? Some general info. As you probably already know, it will take place during the satellite events at the Big Data from Space 2025 conference in Riga, Latvia. The hackathon will be a 2-day event from 9 to 5 on 29 and 30 September. And there are two venues. One is for the main event of Big Data from Space, and the satellite events will take place at the University of Latvia. And there is a page we have created on DevPost where you must register for the hackathon. And this is the page where you will also create and submit your projects. And this is the main page where you will find all the material and all the information from now until the completion of this hackathon at the end of September. And very important, please do not forget to also register for the BITS conference. There is a page for the satellite events registration where you need to register to secure your participation in Riga. This is the information about the venue, the location of the University of Latvia. This is the program of the 2 days. We will start on with the registration at 8 o'clock Central European Time on Monday, 29th of September. And the hackathon will take place at room 301. Please keep an eye on DevPost because more information about the exact program of the hackathon will be released in the next few days. And then the second day is the same from 8 to 7. One correction, it is the time is local time, local Riga, Latvia time. And about the tracks, we have 3 main tracks in the hackathon. One is dedicated to the EO Foundation models that will be explained shortly by Yi Wang. The second track is on weather forecasting models that will be introduced by Franziska Gerken. And the third track by Angelo Zavras, which is focused on the vision language models. Now, the evaluation criteria and the prizes, as we have announced on the DevPost page, we have cash prizes for the first, second, and third place, and we will evaluate the submitted projects in terms of effectiveness, efficiency, novelty of the submitted project, clarity of the methodology, and the impact potential. Now, what you are expected to submit, this is a hackathon organized in the context of a Horizon Europe project with very strict rules. And since we have cash prizes promised, we need to have a full description and a full documentation of each submitted project, so we can facilitate the evaluation process and the work of the jury panel. And we need to have full and transparent documentation so that we have a fair evaluation and a fair process of giving the awards. So you need to create, there is a specific template on the DevPost. If you see it's very easy, I can show you later how to create a project and the steps to follow there. Where you need to provide a full description, including the project title, a description of the project and your motivation, what is the problem that your project aims to solve, how you build your project, any challenges that you run into, some key outcomes, lessons learned, and possible next steps, what you use to build your project, and optional but highly recommended to accompany your submitted project with a video where you introduce yourselves or your team in case you co-developed with a team your idea, to introduce your project and to explain orally what you have built. And most important and mandatory for all participants to submit a GitHub repo because this is the most important part for the evaluation process. And some minimum requirements of the GitHub repo, a README file where you will provide a description of your project, the problem, the approach, and the outcome, instructions to run the code, installation instructions, any dependencies, and execution instructions. Project documentation, which shall include the methodology, meaning the data that you use, the models and algorithms, the preliminary results that you have, plots, metrics, and qualitative insights, limitations, if there are any that you have identified, the code, folder or Jupyter notebooks containing the implementation code, and please make sure that the code is reproducible and has a clear structure. Avoid a messy code that is hard for the evaluator to run. The data that you use and the pre-processing steps, any requirements or environment with dependencies, and the license that accompanies the GitHub repo. Usually we use MIT license, but it depends on the participant. And of course, please feel free to customize and add more information as you wish. These are minimum requirements to ensure that the evaluators have all the information to rerun and produce the results of the project, and have all the documentation to decide who will be the winner at the end. Now I will give the floor to the track leaders. Each track leader will explain the material, will introduce the material they have developed for the track. Then we will have a short Q&A session for each track. And at the end, we will have an additional Q&A session if you have any questions for the overall organization of the hackathon.
Hello again. Let me now introduce the track 1 of this hackathon. It's called the Earth Observation Foundation Models. Let's go to. So in a short summary, in the very beginning. So this task is about exploring Earth Observation Foundation models in whatever interest or whatever ideas or topics that you are interested in. We provide some example topics, and you can also choose on your own. You could, for example, explore fine-tuning strategies of foundation models, generalizability across tasks, geographies, modalities, and so on. You can also explore limitations of current foundation models, explore novel use cases or applications beyond standard or simple academic benchmark on real-world problems, or any other cool ideas that relate to your foundation models. You will have to submit, as Susanna just mentioned, project report, representations, source code with documentations, and so on. The detailed things will be, a detailed template will be provided later. So as a quick background, if you are not that yet familiar with your foundation models, or in general foundation models, the word, foundation model is essentially one model pre-trained on broad data that can be adapted to various downstream tasks. In computer vision, or in general in our task, Earth observation imagery, satellite imagery, area imagery, this is typically one convolution neural network or vision transformer backbone that is pre-trained on big satellite or area data using self-supervised learning. A quick example here, I guess everyone knows of ChatGPT. So this is a language word. The back end, like magician behind ChatGPT is GPT-3, now GPT-4, but in the beginning it's GPT-3, which is one giant transformer model that is auto-regressively pre-trained on broad language data via next token prediction. So GPT-3 itself is one strong foundation model, and with supervised fine-tuning, reinforcement learning with human feedback, we got ChatGPT that can be used end-to-end for many people. So GPT-3 in this case is what we are talking about here, a foundation model. And one note here is that in broad sense, end-to-end foundation models, especially vision language models such as GPT-4o, these are in this sense fine-tuned models and beyond the narrow definition of our foundation model here, which is essentially one pre-trained backbone model. So again, this is one very simple illustration figure about the whole process of about foundation models. So in the very beginning, you have to curate a lot of data from a wide range of resources, curate the data for pre-training, and then start the pre-training in a usually self-supervised manner. These first 3 steps contribute to foundation model pre-training. And after the model is pre-trained, you can adapt this model to your specific task and deploy it for operation. So what are the potential benefits of foundation models? They potentially have strong generalizability across tasks because it has seen broad data. It has probably improved in performance on one or several specific downstream tasks, may reduce the needs for labor data, maybe cost efficiency at scale with partial or efficient fine-tuning. They may have emergent capabilities, for example, reasoning, because they learn the knowledge themselves from large scale of data. These are all those buzzwords of the benefits of foundation models, the hype of current AI. But are they true, or are they always true? These problems or these questions are both very interesting to be explored in the current status. You can also, for example, you choose them as one of the topic that you want to study. And one brief intro about how to build the foundation models. I have just seen the word about self-supervised learning. So usually there's two-stage process of building a foundation model and use a foundation model. First of all, you have unlabeled data, a lot of unlabeled data, and you train a model in a self-supervised manner. This self-supervised could means, for example, masking some part of the image and reconstruct it back, or shuffle the order of some of the patches and then predict the correct order. This is so-called self-supervision. And after this model is pre-trained, you can then transfer these pre-trained weights to downstream tasks with labor data. And here's just some examples of popular pre-training datasets in Earth observation field. From these, you can probably see that most of the dataset are intended to have a global coverage with wide range of sensors and images from all over the world. But you can probably already spot one limitation already. For example, most of the datasets now, they do not cover the ocean. They do not cover the polar region. And this could be potentially one strong limitation of existing foundation models. Whether this is true or not, depending on the real-world study on a specific use case. So how to use a foundation model if we have one already? We could use transfer learning techniques to transfer the pre-trained weights to downstream tasks and fine-tune the task-specific models. You can have several options of fine-tuning the models. For example, you can fine-tune everything, just train again all the parameters of the neural network. You can fine-tune just the task head. For example, freeze the pre-trained encoder because it's usually big and it's already have strong representation already. So you can probably only tune the task head to save cost. Or you can do parameter efficient fine-tuning to enable a bit flexibility of changing the model parameters, but still remain cost efficiency. This is usually fine-tune a small subset of the parameters or introduce some additional adapters or auxiliary heads to help the model tune the weights. Here, I show one example here of parameter efficient fine-tuning, which is LoRA, called low rank adaptation. So in this transformer block, for example, from on the left-hand side, this is the pre-trained weights, so it's frozen. You can freeze it, and this is input. Going through these frozen pre-trained weights, get the output. So you still keep these pre-trained models unmodified. You just additionally add one adapter in parallel to the pre-trained block with low rank matrix, so reducing the rank from the dimension from a big one to a small one, and then scale it back. So these parameters will be much smaller than the full rank matrix, but you have these matrices trainable such that this can fine-tune or adapt the pre-trained model to the downstream task. So one example, specific example about one downstream task, for example, in standard image classification, I here use PyTorch as the standard pipeline. So the standard pipeline workflows are as follows. You just create one PyTorch dataset as usual. You create one PyTorch model, either as convolution network or vision transformer, with the backbone as same as pre-trained model, and the head, which is according to the classification task. And you load pre-trained weights to the encoder backbones, freeze the encoders optionally if you want to do partial fine-tuning, or you unfreeze everything if you want to do full fine-tuning, or you can add adapters such as LoRa for parameter efficient fine-tuning, define the loss functions. If it's classification, then it's usually cross entropy, or binary cross entropy if it's two binary classification, and the optimizer, and start training. So most of the components are standard supervised learning, except that you load the pre-trained weights, and you have to ensure your pre-trained backbone is the same as pre-trained model. And you can optionally add adapters or whatever other techniques that you can help fine-tune the model. So again, another example of dense prediction for in a pixel level. Everything is the same. Create PyTorch dataset, create PyTorch model. In this case, the encoder is still the same as the pre-trained model. But for dense prediction, you don't, one linear layer doesn't work now. So you have to have dense layers. So you can customize your decoder, for example, fully convolution neural network as a common semantic segmentation task head. And you can optionally also process or feed the intermediate features from the encoders to the decoder. You load pre-trained weights to the encoder backbone, the same as image classification, and you freeze the encoder optionally at the adapters, also optionally, define loss and optimizer, and start training. So also very similar to before. Some example foundation models that we provide as a reference. You are also free to choose those that you are most interested in. There are a bunch of foundation models already in the field at this stage. There are modality agnostic ones, for example, Copernicus foundation model, DOFA, FORMAT, and so on. These models can inject whatever channel combinations as input. So it is very flexible, such that you can use it for largest flexibility in downstream tasks. These are vision transformer backbones. We have SAR and multispectral models that they are specifically designed for radar and optical images, but they are kind of fixed. So you have to input 2 channels for dual polarization SAR, for example, or 12 or 13 channels for multispectral images. We have also RGB, like pure RGB images, and also even hyperspectral images and their corresponding foundation models. So you are free to choose any of them, depending on the downstream task that you want to use. So now I will just briefly present one demo. So we have prepared several demos about using EO foundation models, 4 of them. The first one is partial fine-tuning that I just mentioned, freezing the encoder and fine-tuning the task head on a classification task. The second one is partial fine-tuning on a segmentation task. It can be also used for regression, very similar. And the third is a simple parameter efficient fine-tuning notebook using LoRa that I just explained. And the last one is no fine-tuning notebook. You simply use the pre-trained model as an image encoder and to inject in image representations and to do image retrieval. So you can start with these demos to work on your own project later. Here I will just show one example. Let me share again another screen. About the notebook. Okay, let me simply share all. I think it's here. Yeah, so if you scan the QR code, and I think the link will also be provided, you will go to our ThinkingEarth Hackathon GitHub repo, and then you can click into track 1, which is my track about EO foundation models. Here are some simple illustrations as well, and I will quickly go through one demo. That's it. here. So one demo about track 1 image classification. So this notebook can be directly run on Google Colab, for example. You would probably benefit with GPU enabling, but it can also be run on CPU. It's just slower. So, but it's the dataset is small, so it's fine. This notebook demonstrates the simple use case of one pre-trained foundation model backbone on one image classification task. It will include, as I just mentioned, loading a classification dataset, loading a pre-trained foundation model as an encoder, build a classification task head, fine-tuning the model with while freezing the encoder as very simple partial fine-tuning, test the trained model on for quantitative performance metrics, in this case accuracy, and inference on some samples. So I will directly go through without running it on Colab to save a bit time. But all the things will be same, identical here. So first of all, we in all my notebooks, I will use TouchGeo for dataset and for most importantly dataset loading, and it also supports some foundation models, as you will see in the README file of all the examples. So which is very convenient if you simply want to build something upon these foundation models without modifying the parameters, the architectures themselves. I will show in this. So we first install the TouchGeo library just via pip, and then import some basic libraries. For example, Torch data loader, matplotlib for plotting, TQDM for progress bars, and datetime for time management. Define the device and load the dataset. So we use Copernicus bench Euroset S2 as one example. You can find other datasets, example datasets in the README file as well. You can also choose whatever dataset that you find most interesting, or in your specific use case in the field that you are working on. This dataset is one simple classification dataset based on Sentinel-2 images, derived from Euroset, the very popular Sentinel-2 classification dataset, with multispectral images, 13 bands, 10-meter resolution, and 64 by 64 pixels for each image. And each image is one from 10 land use and cover classes, single class image classification problem. So we import the dataset from TouchGeo. So it is very convenient. You don't need to download the dataset and create your own data loader. Just load it from TouchGeo. And we import Cornea here as for data augmentation. And defines, this is 13 bands. So we define mean and standard deviation for each band. And define data augmentations. Here it's random resize cropping. And random horizontal flip, very standard, and normalize the images according to the mean and standard deviation. And for testing, we don't do random resize cropping, just resize and normalize. Very standard, and define the train validation testing dataset. One good thing is that for TouchGeo importing, if it's not downloaded, you will just need to enable the downloading argument such that it will automatically download everything for you. Yeah, we can optionally check one data sample, for example, this one. Just plot it, and you can see that this is a Sentinel-2 set imagery with the scene of permanent crops. Yeah, we can create a data loader. This is standard as in supervised learning. And this is the most important part. We load pre-trained foundation model. For most public foundation models, there are generally two ways to build it and load ways. The first way is to load from their official GitHub or Hugging Face or wherever else their source codes. This enables the most flexibility to adapt to your own scenario if you want to modify the foundation models themselves. Or you can load from third-party toolboxes that is already wrapped up. For example, TouchGeo. For example, also Hugging Face transformers. These third-party toolboxes that enable you most convenience. So in this demo, we will illustrate both ways. We choose Copernicus foundation model, as I just mentioned, as one foundation model used here. This model itself is a little bit more complicated than other models because of its extensive power. most other foundation models will be just simple. So in the first option, we load the model from official source codes. In this way, simply just git clone the official library, the official GitHub repo, and define some system path such that you can import the modules as you want, and create the encoder. And this is the model is created, so we can now download pre-trained weights from also public paths and give it somewhere, and then load the pre-trained model, a very standard torch load, and model.load state ticket. Yeah, we can optionally preempt the encoder to C. So it's just some big transformer, vision transformer with a lot of specific blocks, and also the standard transformer blocks. So that's the first option of cloning from source codes. The second option is load from TouchGeo if you don't want to change anything within the model. So in this case, it's simply from TouchGeo.models, import Copernicus Foundation model base, Foundation box weights, and you can check TouchGeo documentation for illustrations on other models. And creating the encoder is just one line of code. Because we define the weights parameter, so the weight downloading, pre-trained weight downloading is also automatically done here. And we can print it. And this is identical to the previous one. So after we have loaded the pre-trained weights, we can then start building the task model, as we just show here. For example, usually if a pre-trained model, if its weight is available, they will have a built-in head or whatever fully connect layer in the last layer, which is usually identity, because we want to have the pre-trained encoder task agnostic. So directly the features are going flow through the model, and in order to solve the task, we need to build a task-specific head. In this case, it's one linear layer to output class probabilities. So during training, we can either fine-tune all parameters, both in encoder and head, or fine-tune part of the parameters. For example, only the task head. In this case, we just train the task head, one linear layer. So we build the classification head here. The embedding dimension is the dimension from the encoder. The number of classes is the final output layer. And we just define one additional linear head for the classification task. And because we want to freeze all the encoder, so we turn off all the gradients of the encoder. And we can print log the trainable parameters now and total parameters. So you can see that the total parameters is roughly 140 million, which is pretty big, and the trainable one is only 7,000. So this will then be very efficient for the training. We define the loss, cross entropy loss, R&W optimizer, and start training. For Copernicus Foundation model, this foundation model used here, this is flexible for different modalities. Any model, foundation model, which is very powerful, but it needs some additional metadata to guide the model. So it's kind of increase a bit the complexity. So you can check the source repo or tutorial documentation for detailed instructions on how to use this model specifically. But here I just create one simple example to show you the general pipeline of using the foundation models. So here, for example, this model requires wavelengths of each band and bandwidth of each band, and the date of the image acquisition, and the corner size of the vision transformer. Yeah, and we just define them for this data set and start the training loop. So iterate over epochs, iterate over batches of data samples, get the image, the label, and build the metadata. Here it's the longitude, latitude, the location, the time, the area of that patch, and stack them as one input for the model as well. So then we just, because we freeze the parameters of the encoder, so we don't need to update the gradients of the encoder anymore. So we simply use torch.no gradient to get the embedding vectors, and then use the linear head to get the output probability, 10 class probability, and create the loss, and then update the loss and the gradients. So start the training. Here it's I just stop within several iterations, for example. And for the testing, it's so after the model is trained, it's very similar to supervised learning now. You can build another testing loop, very similar, input the image, label all the necessary parameters, hyperparameters, and get the predictions, get the prediction probabilities, and get the prediction classes, and compute the accuracy scores. So that's very standard. And you can after this step, you can probably get one accuracy score. I don't know, maybe 80%, 90%, depending on the model performance. And after that, you can finally influence the model on several examples. For example, we just choose one sample here and get the image, get the metadata that is necessary, and then similar to testing, get the embedding, get the prediction output class, and plot it and print it. So because I only trained several iterations, so the model is definitely not learning things well. So for this permanent crop image, it is outputting another class. But that will be solved if you train longer and if you explore other better tuning strategies. Yeah, so that's essentially one standard workflow of using one foundation model, fine-tune partial parameters on one image classification task. In these tracks, I provide several other demos, for example, segmentation, which is very similar to classification, except that you now have dense output. So you will then need to build your task decoder for the dense output. Here, in this demo, I have one simple fully convolutional neural network. Just do several convolution and upsampling blocks to get the output probability map. All others are identical to the classification task. You can also build your own task decoder for better performance. And the third demo, I provide parameter efficient fine-tuning demo with building LoRa adapters to the encoder parameters. And this is also very useful if you want to explore parameter efficient fine-tuning techniques. Let I just quickly go through this one. For example, very similar. This one I use radar images as the data set. Again, load precision foundation model, build task model. And what's important here is that we have LoRa adapters on attention layers of the encoder, so which are then trainable. The original encoder is still frozen. So in this case, we use another library called PEFT from Hugging Face. So you can, it's very also very simple. Just from PFD import LoRa config, get PFD model, and to define your config. This is the important thing. So we want to add LoRa adapter modules on the attention layers, so on the QKV layers, and that's it. So here you can also, for example, the training parameter is now roughly 600,000, and all parameters still 140 million. So the trainable parameters on the encoder is below 1% of all the parameters. So it will give you some flexibility of tuning the encoder, but still remain cost efficient. You can here it's LoRa adapter. You can also explore other parameter efficient fine-tuning techniques. For example, training the BIOS, for example, prompt tuning, whatever. You can find all these important resources from this library if you want to explore this task. And all the others is very, very similar to the previous ones. Yeah, and that's it for this one. There's another one in the very end, which is one image retriever task demo that you don't fine-tune the model anymore because we want to retrieve. So the task is that given one image, you just retrieve from one candidate pool another image or several other images that is similar to this one semantically. So you don't need to fine-tune the model anymore because the model is pre-trained. So you can assume their representations are also similar, such that you just encode the representations from the pre-trained encoder that you just do similarity search on the encoded representations. So, and this task you can also evaluate based on the image labels, for example, as one semantic guidance. I will skip this tutorial, this demo for now, but you are very welcome to explore it yourself. Let me just show you the very end. For example, what it looks like in the very end. You have one query image, such as this one, and you query several other images from the pool. For example, this one is annual crop image, and that is the one that it's queried. Another annual crop image, another annual crop image, another annual crop image. So very similar, and it is very successful. Yeah, so that's it from my demo presentations, and I have one last slide to summarize my track. Let me share again. I think it's here. Yes. So a quick summary of the task. As I just mentioned in the beginning, this track is very, very open. So you are generally allowed or encouraged to choose or create any topic that you are interested in related to foundation models. But you have to work on a complete project, including the input, the motivation, the background, why you do that, what's your output, what's your conclusion, what are your insights, your findings, your challenges, your limitations, potential future work that you can derive from this work, and so on. Importantly, with reproducible codes, because that's important for us to evaluate your result. Topics, I have some example topics on the GitHub repo that I just mentioned. Here, just list some of them. For example, do foundation models provide more benefits on some task types while less on some others? For example, is it better on classification? Is it better on semantic segmentation? Is it better on one specific task that's your application is focusing on, like forest monitoring or whatever others? What are the practical limitations of existing foundation models? They have a lot of benefits. People always claim that, but do they have practical limitations on your specific application? Or what do you see as other practical limitations? For example, is the model just too big that you cannot run on your mobile phone or whatever? For example, and can one foundation model trained on one modality be transferred to another one? If the model is trained on optical imagery, can it be transferred on radar imagery? For example, how do foundation models perform across different amount of labels? If you do fine tuning, if you have like 1 million labels, probably you don't need foundation models anymore because your good quality label is a lot. If you have only one or several labels per class, maybe you will quickly overfit. That's also another issue. So how do the foundation models perform across these different scenarios? And you can explore parameter fine-tuning techniques, as I just mentioned. I showed Laura in the demo. You can also explore Bayer's prompt and other techniques that could be interesting, or explore novel real-world tasks beyond benchmark suits that we provided and the standard academia provided in your real-world, in your own task field. Yeah, so there are a bunch of other topics that we provide as examples in the GitHub repo, but you are also free to build your own topic that you are most interested in. Just relate to your foundation models that we provided or one that you are interested in. Some useful materials, the hackathon main page, Susanna just mentioned that and show that you have that already. Task 1 resources, I just mentioned that GitHub repo, and some submission introductions. Susanna also just mentioned that. And we will probably have one template for the submission soon. Yeah, I think with that, I think that's it for my track. And where if you have questions, you can ask now, or we can move on to the next track.
Okay, so my name is Franziska. I introduced myself beforehand already. I have a first slide. Okay, just kind of, we already had the roundtable, but yeah, this is me. This is also my supervisor, who's like also responsible or part of the Thinking Earth project, Laura Leal-Teché. Exactly, and we are setting up the second track of the hackathon. The task summary for our track is to compare the capabilities of state-of-the-art weather forecasting models. So you will be exploring mainly downstream tasks in the range of weather forecasting, and more specifically, like explore limitations and strengths of existing weather forecasting models. And we want to focus on evaluation frameworks here. So we want to kind of apply existing models on downstream tasks on smaller data sets and see like how they work there, how they perform, and what are the limitations and what are the strengths. It might also be interesting to maybe analyze the effect of the architecture on the performance. So maybe find a reason why the performance is better or worse. But there are also like any other cool ideas related to weather forecasting, which can be included in the whole task of the track 2.1. What you will be submitting is very similar to all the other tracks. So this is kind of streamlined. You will be needing to submit a project report, a presentation, and then also the most important part is like the source code, with documentation as a GitHub repo, as the base of everything that they did in the project. Okay, we heard a lot of things in track 1 now about like Earth observational data. I want to give now, I want to introduce this track, but like starting on weather forecasting and explicitly kind of opening up like the parallel track that we have in Earth science, which is not Earth observational data, so not images, but it's kind of reanalysis data. And I'm not quite sure how much the knowledge of everyone participating in the background in the hackathon is. But I'm gonna start like very basically, and I'm gonna kind of introduce like 3 questions here. The first one, which when I started to work on the whole field of Earth science, is something that I find quite interesting and important to maybe quickly mention. What is the difference between climate and weather? So here we always say climate science, weather science, I don't know, there's kind of everything is used, and I think very often it's kind of a little bit confused. So I put here like one definition, which I think explains it quite well. So weather, whenever we talk about weather in climate and earth science, we refer to short-term atmospheric conditions at a specific location. So we measure variables such as temperature, precipitation, wind. Climate is something which is more long-term. So on the other hand, weather, this is kind of the long-term average of these weather patterns for a region, which is typically measured over decades. So I think as a summary, weather is like short-term and climate is long-term. And what we're going to do here is weather forecasting, but more specifically, all the models that are currently working on weather, so weather data, are mainly in the field of medium-range weather forecasting. So I also wanted to explain this one. So what exactly is medium-range weather forecasting? Medium-range weather forecasting involves predicting the weather, so short-term weather, and more specifically, this means that we have like predictions up to 3 to 15 days. So this is called medium range, as it's not explicitly like just the next couple of hours, but we are able to predict 3 days ahead or even more, like up to 2 weeks. But we're not doing like long term, which would be months or maybe even years. So medium range weather forecasting is, I think, one of the center parts, which is in weather forecasting something that current state-of-the-art models are focusing on, because we have like very good data sets, which are giving us a lot of possibility to kind of extract patterns, to understand the patterns, and then to predict in a medium range the weather patterns. Exactly, and here we have like complex numerical or AI-based weather prediction models. I think one of the shifts, as in every field, but I think here in climate it came a little bit later than in images and languages. We started with like numerical methods, like in the 80s, where we have like numerical methods which are like very computationally heavy, who kind of predict the weather. And there's now recently a shift to AI-based models, which are using all the deep learning architectures and try to learn from the data sets that we have available for weather patterns, and they try to kind of learn in a machine learning framework the patterns and not solve the problem of forecasting numerically, but doing this in a learned fashion. Exactly. So what we try to have, like we're gonna understand like the patterns that we have in the weather, and we analyze like current observation in order to predict future states. This is like the the thing of weather forecasting. I think it's a little bit different to everything that Yi has been explaining, because this is very much to satellite data, analyzing images, which is much more related to kind of the whole image or like computer vision setup. And the task in this track is going a little bit more to tabular data. And what do I mean with tabular data? We are gonna work here, like we have the second parallel world of Earth science, where we have like not images that we want to analyze, but we have the measurements of weather patterns. And this is called, like, everybody that, like, everything that we are going to work on and state-of-the-art models are working on is reanalysis data. And the very important name here is ERA5. ERA5 is a very big data set that all the models are trained on, which in the end is reanalysis data, which combines a vast amount of historical weather observations with a single consistent weather forecasting model to create a best estimate of the global climate over decades. That means, I think the last sentence is quite interesting, it's essentially a comprehensive archive of the past weather, creating a continuous gap-free record of, often referred to as a map without gaps. So this is kind of, in the end, the reanalysis data is also based on satellite images, but it's kind of a produced data set, which is giving us a very nice record of the global weather over decades. And the ERA5 data set is the one that most of the state-of-the-art models are trained on. And this is also one that we're gonna have in mind, or you will like be handling here in the track as well. So you will interact with the ERA5 data as well. I have, before we come to the ERA5 data, I want to quickly summarize a little bit. So we have Earth observation, the field of Earth observation. There are like many models. Some of them are included here. They are much more recent one also, but this is kind of a set of like MOCO, SECO, SSL4EO, Satlas, Pre-train, DOFA. These are kind of Earth observational models. And then after 2024, of course, there are other ones. And the parallel track that I'm talking about, that I have been introducing, is the ones working on weather and climate, and all of the models that are here in green are ones in medium range weather forecasting. And they are not working on satellite data, but they use the ERA5 data set. So we have ForecastNet, which is internally from NVIDIA. We have Pangu Weather, which is quite famous because it's stated to be the first one, or I think it was the first one, which claimed to be better than a numerical method. We have GraphCast, a graph-based architecture from Google, Climax, Neural GCM, and very recently there came out the Aurora, which is kind of a foundational model, not only being trained on ERA5, but also combining lots of other data sources. But all of these ones are kind of heavily based on ERA5, and these ones here, the green part, will be part of track 2. So we're gonna focus on the ERA5 data set here. I have one slide which is very shortly summarizing the ERA5 dataset. I think the ERA5 dataset requires for our track to have like some part in this presentation, because also in our notebooks it will take some part, because you will always need to load the data. You will always need to kind of put them into a model, and this is kind of just something which is heavily, like it's just quite complex because the data is so big. So we're gonna spend some time in the notebooks. I quickly gonna give you an overview. So the ERA5 is a reanalysis data set. It's global, so it means that it covers the whole globe. It's atmospheric. That means it measures like some variables, something as temperature, precipitation, wind speed, humidity on different pressure levels. Pressure levels here mean that we have different heights. So for somebody who's not from earth science, the pressure level, the higher the pressure levels, the lower or the nearer it is to the surface of the earth, and the lower it is, the further up in height it is. That's kind of how you can see it. Exactly. The data is provided by ECMWF. This is the European Center for Medium Range Weather Forecasting, and that's part of the Copernicus Climate Change Service. So they provide this kind of data set. It's covering 1940 up to present, so it's updated regularly. We have a very high spatial resolution, and that makes this data set so nice. So we have a resolution of 0.25 degrees. That means we have data points on like the grid that we create. I included here on the right side, we have a latitude-longitude grid. We have in total 721 times 1,440 points. So over 1 million data points on the globe. And then we have like, they are covering, I think, roughly 10 kilometers near the equator. This is kind of the spatial resolution, which is exceptionally high compared to every other data set. We also have a very high time resolution, so it's hourly data. And then we have a huge range of variables. So we have, as I said before, atmospheric, land, and ocean is covered, so everything is covered. We don't focus on just kind of land or just ocean or whatever, but everything is covered. And then you have like temperature, precipitation, wind speed, humidity measured on like more than 13 pressure levels. So there are like more than 300 variables in the end included in the ERA5 dataset. Exactly. Very often, the models that we're gonna check out here train on data which is going up to 2015. So they train up to 2015. Then we have 2016 and 2017 as validation data set, and really often 2018 is the test data set. Newer recent models shifted and include data up to 2022 for training, and then they evaluate on 2023. So this is something that we need to have in mind whenever we evaluate the models, that we always make sure that we just evaluate on the test data, of course. So the Aurora paper, for example, here is a newer paper, and they test on 2022, I think, and 2023. Exactly. So this is a short introduction to the ERA5 dataset. I come back to this one later. Just one mark that I wanted to do here, or that I wanted to include here, because this is something that you're gonna come across when you start working on the track 2. And the data for 1 year, I summarized it here. If we have like 2018, we're gonna include like only 6 hourly data. So we have like 4 data points per day for all of the days of the year. This data set is already 400 gigabytes. Then if we include like the whole data set from 1918, which is a time range that a lot of models are trained on, 1918 to 2018, we have like 16 terabytes of data. So you can see the problem here is really often that the data, which is great, it's big, but it's also quite difficult and complex to load the data and to train a model on it. Even like small models, the data set is like so huge, just the training, like this vast amount of data. Processing one data point is a lot because we process the whole globe, and you saw that there are like a lot of data points here on one day and one specific time, but then also you have like all the measurements across a year. So this is kind of scaling up quite a lot. So the ERA5 data set alone is kind of a very complex, super interesting data set. So I think it gives us a lot of possibility to extract weather patterns, but this has to be done kind of in a very efficient day. Otherwise, you're just gonna spend a lot of time on training and prepping the data. Okay, so this is just kind of one slide summarizing again of how our data looks like. This is how the models are trained on. So the models have like this kind of net, which could be like a graph with like different nodes on the globe. And each of the points here is a spatial location. Out of these over 1 million spatial locations that we have in total, and they contain a bunch of different variables measured. So this is kind of how you can imagine them. The orange ones are surface ones, temperature at 2 meter heights. Then you have like the U variables as atmospheric variables on different height levels or pressure levels. So here you can see U500, U850, U925. So this is kind of different pressure levels for the same variable of U. Typically, you always have U, V, T, and Z. Sometimes there's like a variable Q included or a variable R. Exactly. So this is the data set. Now let's come, before we're gonna check out the rest of the track, I want to quickly introduce WeatherBench 2, because I think all the weather models that we train on, that I presented on the one slide where we had the timeline, all of them are trained on ERA5. But I think the problem in weather forecasting and medium range weather forecasting is that these models are typically not compared very well across each other, because it's just very difficult to load the data and to evaluate the data. It just takes a lot of time. So even if you don't train it, this is a lot of work. And there's like very minimal effort to have like a proper comparison across models. So really often a paper is introducing their model. They trained it for like a long time. They put a lot of computer resources in there, and then they may be compared to like the numerical method, and they may be compared to one other model. But typically what is missing in the field of medium range weather forecasting is like a nice evaluation framework where you kind of evaluate against other baselines, just because everything is like so expensive. WeatherBench 2 is one of the missions here, which started an open source framework and benchmark for evaluating, comparing the skill of data-driven machine learning models against traditional physical or physics-based models for global medium-range weather forecasting. So this is nice. We have like a starting point here, but there are a lot of models missing. They offer an evaluation framework, which is quite difficult to use. So I think compared to like specifically the language area and computer vision area, like the whole evaluation here in medium range weather forecasting is at a very beginning stage. And this is also kind of the part, or like the reason why we set up the track 2. Exactly, the track 2, or let me maybe quickly read you like this one thing, which is taken from the Aurora paper. Aurora pre-training and comparison. So of course, every paper also in like other fields in like machine learning are now reporting the time of training. I think this is especially important for like the medium range weather forecasting here. They say the training of Aurora is comparable to GraphCast, one of the big models from Google, which is 4 weeks on 32 cloud TPU V4 devices. And it's faster than the Pangu weather model, which is about 7 weeks using 64 GPUs. And I just wanted to include this one here. So to train a model to kind of the performance that we have here, like big companies use like the very big GPUs, like the 64 GPUs, which I mentioned here for Pangu weather. I think they have like at least 32 gigabytes. And then they train on a bunch of 64 together, and they still train for about 7 weeks to get the performance of the model that they're reporting in the paper. Things are getting a little bit more efficient, but still this is kind of a long time. And this is also, it's like a big and many GPUs needed. We need a lot of time, and this is just very compute heavily. So what we decided in our track in order to work with these models is not to train anything on our own, because only just like loading the data and training on the data, as I explained before, is taking a lot of time. So what we want to do is we want to evaluate existing models. And I think this is already quite a big task. I think it's super interesting because, as I explained before, there's quite a gap in the literature on kind of properly evaluating these models on era 5, but then also on like downstream tasks. There are many downstream tasks where you use era 5 variables, and then you put them into kind of, or you try to get like some weather event, you derive it from the era 5 variables, and then you have labels such as cyclone tracks, for example. So you're gonna take the prediction of these models, they predict era 5 variables, you're gonna derive the cyclone track from the prediction of this model, and you're gonna compare to the ground truth data. And this is giving you like an application or a testing of how well the prediction of these models beyond the metric that we introduced for era 5, how well they work in real world applications. There are some efforts in recent models. For example, here you can see GraphCast, which include like some evaluation on downstream tasks. So here, for example, they do the cyclone tracking. There's like one nice data set, which is giving you some labels of cyclone tracks. And they're gonna evaluate on atmospheric rivers, and they also evaluate on extreme heat precision. You can see here that they evaluate their own model, GraphCast, versus the HRES, which is a numerical model. So this is kind of one comparison, which is quite interesting. I think it's also kind of showing in their evaluation here that GraphCast is outperforming, like the black line here, which is the other model, which is really nice because they test the output of the era 5 variables in an application. But what's missing here, and that's I think quite a nice example, they don't compare to other models. So what we want to now do, or what we ask you to do, is in order to select a couple of models of these medium range weather forecasting models and set up an evaluation framework, or maybe 1 or 2 interesting downstream tasks, and just make a proper structured and complete comparison of the performance of these models. So you will handle with data sets such as the cyclone tracking data set, and there's like data sets for atmospheric rivers and extreme heat, or like ways of how you can derive it from the era 5 models. And you will need to kind of set up like a proper and structured way of how to compare these models. And I think this is a feasible task for the track 2 for our hackathon. I think it's a super important task for like the whole field. I think this is coming up in the next couple of years. There will be a lot of effort in kind of setting up a nice evaluation framework for all the models that we're currently seeing coming up. And this is definitely going in that direction. Okay, so now I included, or I hope I gave you a nice overview of where we want to go with this track. I prepared some materials for you to start with. Let me quickly introduce. So we have like the Git repo that Yi was already showing you. And we have like the track 2 folder in there. What the main resources that are included in there is an era 5 dataset notebook, which is giving you like a workaround or like an introduction to the era 5 dataset. And we're gonna provide some example data from 2018 and probably also higher ones that you can download. And then this notebook is giving you the possibility to check it out and just to understand this kind of data, because you will need to use these variables in order to apply them to the downstream task. There will also be a notebook, or there is a notebook, which is introducing to weather forecasting models. This is giving you 3 models. So we're gonna have the SFNO model, We have the Pangu weather model, and we have the Aurora model. All of these models give you pre-trained model weights, which is not the case for all of the models. And then exactly, I'm gonna explain some more details about the models here. But I'm gonna introduce like the inference code here so that you can put in the data sample and you get a prediction from these 3 models. And last but not least, we have a Docker setup, because for all of these models, you need to kind of set up specific things. So we have a Docker setup which has everything for these 3 models in one Docker. So you can start working with that, and then you can extend it to your need. Exactly. Let me go as similar to as he did it to the Git repo. Okay, I think you can all see the Git repo, right? Okay, I assume it's fine. Otherwise, somebody will probably let me know. Okay, so here's the track 2. I'm gonna show you like the contents in there. So here we have like the folder with the Docker is just the Docker image set up that you can use by yourself. So this is something that you just need to kind of figure out whenever you start working and you want to kind of evaluate stuff. The most interesting thing here is like the 2 notebooks that we have here, Era 5 and the weather models. I'm gonna start with this one here, the Era 5. As I said before, we're gonna spend some time to understand the data. This is also the case why I included like the explanation of what is Era 5, what is reanalysis data. I introduced kind of like, you can just work through this one here. It's just giving you like some code where you can kind of use a data loader that we set up in order to load the data, and you can just check out how it looks like. So you can check out, there's a lot of metadata, there's a lot of things with like the timestamps if you want to kind of select a specific timestamp, which is quite important when you want to kind of evaluate things. There's like a lot of libraries that you have to kind of play around with. I wrote a data loader, which is giving you the main functionality to just put in like a string, which is giving you the time, and then it extracts the data from the data file that we have. You're gonna have some metadata that you can read out, and you're also gonna have the possibility to get the data specific for one of the 3 models, because every model has a different setup of how they take the data. So I prepped ways that you can just put in the model that you want to use and the timestamp, and you just get kind of the data in a format that is kind of usable for this specific model and for inference. So this should be quite easy. This one here is like just a lot of explanation, some links, and kind of links to kind of the code, which is giving you access to the Era 5 data set. The other one is the weather models. And I think this one here might be quite interesting whenever you want to evaluate models. I think it takes a lot of time to just understand, get the code, and get like the inference running is like very specific to how they set things up. And what I wanted to explain when I interrupted myself during the slides, the problem here for medium range weather forecasting is that not only the evaluation framework is in the very beginning stages, but also kind of sharing stuff about the models in computer vision. And I think for satellite images, it's much more usual. It's very typical to include like checkpoints. It's very typical to just kind of have a very easy way to train the model, to load the model, to do inference on the model. For the medium range weather forecasting models, this is often quite difficult. Not always there are checkpoints. So for SFNO, there is a checkpoint. Pangu Weather allows you to do inference. They don't share like the whole code of the thing. Aurora is quite open. They share a lot of things. They also share checkpoints, but many other models, GraphCast, for example, is quite difficult to get kind of checkpoints to get the model running. There are initiatives to set this up, but yeah, some of these are like more complex. So I included here the ones which I think are the most easy and which I would probably start with in your case. You can always extend it to other models as well, but just make sure that you probably spend a little bit of time, and I would always double check if you have like pre-trained weights, because training this model on your own is just not an option for our case here. Because this is just kind of beyond the scope of the hackathon, and probably also beyond the scope of every personal GPU setup at home. So here we have like the notebook, which is introducing the weather models. I have like the data setup. I included again like the data loader here, where you can see you have like the model flag. So you're gonna specify which model you're gonna have, and then you can just use the data in order to load it. I commented it out here, but you can just do get data. You just have a date, for example, the 2nd of January in 2018 at 6 a.m. in the morning, You put this date in there as a string. It's kind of converting everything to the timestamps. It's getting the specific data from the data that you have in the background. You specify the model Aurora, and then it's giving you a specific output, which is here like a batch. And then you can put it into the model and you can get the thing. I included the paper link and the GitHub link for the Aurora model, and I do similar stuff for Pango Weather and SFNO. So here you can just see everything is wrapped the way that people are using things. The Aurora model is loading just kind of the Aurora GitHub here, or the package that we installed in our Docker image. The Pango Weather is not providing full code so that you can run it yourself in PyTorch, but they wrapped everything around an ONNX model. So what we need here is we need to kind of load the ONNX Pango model, which is just a wrapper. So you can just kind of put stuff in there and it does the whole magic and it gives you an output. You cannot access like the model itself completely. This is kind of just not open source. There's a lot of discussion on implementing the Pango Weather model yourself, but I think this is kind of the safest way to just do inference with this model, and the inference setup is included here. So we have this in the background, which is the code here is in models, where we have the wrapper for the ONNX. Then again, you just load the data set and you can just run it with the ONNX session here. So you run it, you have input and output data, which is the output from the data loader, and then you can just get the prediction of the Pango Weather model, which is also pre-trained here. So both models use a pre-trained version. And the last one is the SFNO model. Also here I linked the paper and the GitHub. The setup here is also included in the Docker, so you can just install the Makani code base, which is the code base where SFNO has been developed in, and they provide an open source implementation of the model. You can also download the checkpoints here. I can very quickly go on the link, or let me do it like this. Gonna put in another tab. Yeah, so NVIDIA has like an open source, exactly an open source checkpoint for the SFNO model, which is included here, the SFNO 30 or 73 channel small version, and here you have the checkpoints. So you will need to kind of save them there locally, include them here in the repo, and then you can just load them. You can load the config, you can initialize the model, and then you can, similar to how you usually do it in Torch, you can just kind of load the checkpoint into the model. The data loader again gives you the data in a format that can be processed by this specific setup of SFNO, and then you can just get like the prediction output of this model. Exactly, this is the setup for the models, which you can see here. I think this is giving you like a good starting point. Let me maybe go back to the slides. Exactly. So what I try to have in the notebooks here is to kind of give you an explanation. I think if you work through these ones and you understand there are 5 download the data loader and doing inference with like these 3 models, you have like a very good starting point on, okay, this is kind of the current setup. You will see that things are like very different. Every model does like a little bit of its own. But then I think you have like a good starting point where you can start thinking about what do we want to evaluate. There are like a couple of, all the papers do like, most of the papers do some applications. But not everybody is doing all of the applications, and they never compare to each other. So you can get a lot of information from the model papers, what you could do for the track. Exactly, and this, let me just jump. This we explained. Exactly. So I think now the task and the topic for the track 2, as I said in the beginning, it's all about weather forecasting models. However, the specific topic is open and up to you. So what we want you to have is we want you to evaluate existing models. You can use the 3 that we have here, set up a framework, set up a task, and just kind of do like a structured and comparable framework where you evaluate and you compare these models. You can, of course, extend it with other models that you find interesting. There are like many other ones out there. You can also kind of define the task on your own. You can define kind of the metrics on your own. You can define a lot of things. But this is kind of, I think, a good starting point. The goal of the task, again, is to identify strengths and gaps in current approaches and just have a structured way and a structured evaluation of how good are the models, maybe in specific regions. For specific downstream tasks, are there maybe 2 downstream tasks where one is very good and the other one is not very good, and then another model has like maybe the opposite I think there are a lot of things which are not known yet about current state-of-the-art models, which can be explored in this track. So topics, as well, I suggested a couple of ideas here in what direction you can go. You can always define this on your own. You can always come up with something else, but as I already mentioned before, the main idea and the topic should be to pinpoint specific areas maybe where certain models excel and where they fall short. This could be with respect to a specific region, because the error 5 is globally, maybe some region is better than another one. And with respect to performance over varying time horizons, so this would be the prediction, the lead time of the prediction. So am I maybe better in predicting just short term, so maybe 3 or 4 days, than 10 days? And then the other one is the ability to predict specific phenomena. So extreme weather events, cyclone tracking, this is something that I showed before on the slides. And the idea here is to establish a framework for evaluation of downstream tasks. So this could be something, establish a suitable metric to compare performances across different modes or models. I think this is also something there hasn't been a lot of thought about kind of how properly evaluate these and which metric could be. So there are always standard metrics, but I think this is also quite interesting idea of how could kind of approach the track 2. And then maybe last one is then explanation in the model architecture that might cause a bad performance. This could also be something interesting to check out. But of course, everything is up to you. So you just define your project and you just set up a nice and structured evaluation framework. Okay, useful materials is the last slide. Similar to as what Yi also showed, we have the hackathon main page, which is linked here again. I linked you the track 2 folder on our GitHub repo. And then also the submission instructions were introduced at the beginning, and the submission templates will be released soon. So everything with that will be released all together for the 3 tracks. Okay, I think this is all from my side for the track 2.
Moving on to track 3 for Eurovision language models. So fortunately, Yi has already covered a lot of nuts and bolts in his presentation of track 1 about foundation models. So I will keep it short and provide some complementary information about vision language models and track 3. Okay, so the task summary, the main focus of this track is to explore the capabilities and limitations of vision language models for Earth observation. In this context, one could explore the zero-shot performance of such models on unseen geographies and sensor types, try to characterize and mitigate failures such as hallucinations, generalization, etc. Try some novel applications such as automated change detection and report generation, and of course try to complement those model encoders and align some non-RGB modalities that are super useful for the downstream tasks of Earth observation. And last but not least, you could explore ideas of your own. At the end, one should submit, as already stated, the project report, the presentation, the source code, along with the respective documentation. Now, some background about the vision language models in general. So, a vision language model learns a joint multimodal representation space for vision and textual data, which allows for downstream tasks such as direct comparison, retrieval, generation across the featured modalities. Now, there are two main paradigms in the context of the vision language models. So the first one is the contrastive alignment models such as CLIP. They essentially align the image and textual embeddings in a shared embedding space, and they try to bring closer the respective image and text embeddings from the same sample, and the non-matching pairs are pushed apart. Then we have the generative models such as Lava, which essentially fuse a pre-trained vision encoder, which is usually a clip vision encoder, with a pre-trained large language model. And it learns to generate text conditioned on visual input. Now, on the GitHub page of the project, you could find a demo on the track 3 folder. We have some examples where we demonstrate open vocabulary, remote sensing image classification, remote sensing image geolocalization, cross-modal retrieval, so image to text and text to image retrieval, and RS image captioning. In order to demonstrate those use cases, we used a dataset that we published recently. So it is the dataset Gaia, which you could see over here, cited. It's a pretty small but diverse dataset. It covers the last 25 years and it features mainly events, so earthquakes, fires, floods, etc., that happened across the globe. It's, as I said, pretty small in size. It's only 25 gigabytes, so you could use, you could use Google Cloud, Google Colab, to train your model, fine-tune your model, or use this dataset in general. Of course, you could use other datasets that you prefer or that are more valuable to your final goal. On this QR code, you could find the GitHub repo and the respective information. Now, some details you have already seen. So the dev post where you could find information about the hackathon in general. The track 3 resources, so the demo I just mentioned, along the README file with some extra info, and the submission instructions and the submission templates have already been mentioned. The last one will be released soon. So that's all for this track. If you have any question that I could answer.
Now we mentioned at the beginning some general details about the hackathon, the venue, dates, and registration requirements. As a reminder, before we close the webinar, please do not forget to register on the Big Data from Space website on the satellite events, and in the registration there are several options to select a tutorial, a challenge, or a hackathon. Please don't forget to register for the hackathon there as well, in addition to your registration in the dev post. And from now until the end of September, please keep an eye constantly on dev post. I will also contact all the participants that I already see in the dev post page to confirm some information that I need to send to the Big Data from Space organizers, the organizing committee, in order to facilitate the organization and to cross check and confirm the registrations. I will need everyone's name and surname and email address to forward this information. So keep an eye on DevPost. We will reach out to confirm the logistics. In the coming few days, we will have also more instructions from the BITS organizers. And you will find all the detailed final instructions on DevPost. About the templates mentioned by my colleagues, as I mentioned at the beginning, the submission templates, as I mentioned at the beginning of this webinar, we will use DevPost for the submission of the project, and following the DevPost template there, we will add the detailed instructions on what this project submission should include, the minimum requirements and the minimum requirements for your GitHub repos, so that you all know exactly and you have in written what material you are expected to submit for the evaluation. Thank you again for joining this webinar, and thank you for your interest in participating in the ThinkingEarth Hackathon. Hopefully we will see you in Riga. We have 2 days dedicated to this event. The first day will be the last mile, coding last mile, and the final preparations of your project and the submissions. And the second day will be dedicated to the presentation of your projects and to the pitches. And then we will share more information over the next couple of weeks regarding the evaluation process and when the participants, when the winners of the hackathon will be announced. Once we have a final confirmation of the participants and the juries, we will share all the details on DevPost. So good luck with your projects, and we will be online to support you over the next 3 weeks. If you have any questions, you can reach out through DevPost or via email. We will share all the information for you. The recording of this webinar will be available for you to rewatch, and we will see you hopefully in Riga on 29th of September. Thank you very much.